Good afternoon and welcome to MAE 113 Calculus for the Liberal Arts. My name is Richard Kohar and we just finished doing quiz number 4. Hopefully everything went well. If there are any questions, please feel free to send me an email. We're going to be covering some more material today. There are, because of, there's some people who have academic accommodations. I'm not going to release the grades right away. I will review them after the class and then I will allow them to be published. So hopefully that answers questions like that. We covered questions that were from the assignment. We covered questions that were from class. It's a nice mix. Hopefully there was enough time. If you feel that there wasn't, send me an email. I definitely want to hear how you guys are doing, or if you, but yeah, just send me an email about the quizzes and stuff like that. Yes, excellent. Partly because we're doing second derivatives in that quiz, and so you would need at least another minute to do a second derivative, so there's some more time needed for that. Okay. And then the other thing is again, if there's questions or you were stuck on questions from the assignment or whatever, make sure that you utilize the office hours as well. We have office hours on Thursdays after class. It's up to you. You can email me. I can send you. I can talk through email as well. I can send. I can write out stuff by hand or type it out. So that's not an issue. But it's up to you. It's your call. I'm comfortable answering questions either in office hours or by email. So. Okay, so what are we going to do today? We're going to do lecture 14. Okay, yes, that's obvious, but we're going to do antiderivatives. So today is the 9th of February. Is it possible to keep the 15-minute time length for all quizzes from now on? I intend to keep it at 15 now, unless the other sections decide to. When will we be allowed to see that grade? There's some academic accommodations, so they require a little bit more time, so I can't release the grades until a little bit after, and I didn't know how to release it until they were finished, so I'll check the grades after, and then I will publish them. Like I said, there's people that have academic accommodation, and so they don't finish writing at the same time. So hopefully that answers the questions. And again, I'm dealing with a bit of a 30-second delay, so if you type a question, wait 30 seconds and I might see it, and then there's a response. So okay, Nick, ethics seems to be okay. If Mr. Sellers, if that's okay with you, it's again because of we have other people who have academic accommodations. The other thing too is it gives me a chance to see the answers, and then I can adjust accordingly, so it's not as much of a shock if there's something wrong. Okay, so we're going to start off with a simple idea. We've been working with derivatives, which has been looking at changes in rate of change. And so if I have this very straightforward polynomial, let's say x cubed, and I want to take the derivative of that while using our power rule, we know that we can bring down the 3 in front. And then we have x squared. Okay. As for one of the questions, yeah, just send me an email if you think that there was something that was awry or wrong. And I'll be able to, I can't really do anything at the moment. I'm at a piece of paper. So make sure you send me an email. Okay, so this is our derivative. And if I take the derivative of that, just using I have nx to the n minus 1 then I'm just looking at the chat too. Good. Send me emails. I'll be spammed. It's good. And not spammed, just inundated. That's okay. It means that I know that you guys are actually taking responsibility for this, so that's good. Okay, so we have the derivative, and this is our power rule. Now, the question is can we go in reverse? We can differentiate, but can we get from this function back up to the original function here? So in this case, they've gone from a derivative when we're going this way, and if we're going backwards, they call this the antiderivative. Okay, so what do we notice when we are going from, when we're differentiating, we notice that we're going down a degree. So we've gone down from, say, we have 3 down to 2. So if we want to get back up to the original function, it means that we should be increasing the function by 1 degree. So that's what we'll do. We'll say that instead of going from x minus 1, we'll say that it's x n plus 1, because we're going up a degree. And then, what's another issue that we have? Well, we have a constant here, and we have a constant of 1 as well here. How could we potentially get this to cancel out? Well, we brought this down in front. Instead of writing it in the numerator, what we'll do is we'll put the plus 1 in the denominator. Okay, so this kind of will give us our rule. So for instance, if I wanted to integrate, say if I had an integral, or sorry, I'm already letting some of the terms out of the bag, but I gotta be careful. So for instance, if I had, say, x to the 4th, then if I want to go backwards, I'm doing the same thing. I'm going to have x to the 5th, and then I'm going to have in front of it here, not 5, but it's going to be 1 over 5. And we can see that this works, so that when we have 1/5 x to the 5th, when I differentiate it, I bring the 5 down in front, so that when I'm differentiating this, I have 1/5, and then I have the derivative, which is x to the 5th. So the 5 comes down in front, and then I have x to the 4th. So that cancels, and I'm left with x to the 4th. So that works. Okay, now one of the issues that we have is when we differentiate something. So for instance, let's use this. If I have x to the 1/5, x to the 4th, plus, let's say 2, if I differentiate this, the 4 comes down in front, so I get 4/5 x to the 3, and then make sure that did I differentiate that correctly? So the 4 comes down in front, and then we reduce the degree, so I got 4/5 x cubed. And when I differentiate the constant, derivative of a constant is 0, so there's nothing here. This is the same problem that we have, that if we're going backwards upward, we're going up, or we're going back to the original function, that if I use my rule using this, when I get back to the original equation, if I'm integrating, or if I'm finding the antiderivative, the problem I have is this constant. Because when I differentiate, I lose a little bit of information. So when I differentiate, we lose information. So what we end up having is that when we're going backwards, that we won't actually know what that 2 is. So that is missing. So it could be any number. So when we do this, we end up writing plus a constant. So that is our rule. The only way that we can get this back is if we're given that piece of information back. Okay, so I've talked about this constant and why we have it. Now let me talk a little bit about the notation. Sorry, could you explain how you did the antiderivative for that example? For which one? I have, let's say, let me just number this. I have 1, let's say I have 2, and I have 3. So which one was it? Okay. It was just a misreading. Okay. So, let's just talk a little bit about notation then. No worries. I will take my time through this because this can be, I mean, once you get used to it, it becomes natural that we end up differentiating and then anti-differentiating. So we have this notation in terms of how we are taking the derivative, and so this is the this is the derivative, taking it with respect to x, and over here, to symbolize that we're going to take the derivative, or sorry, with the antiderivative, let's say I have my x to the n. And I want to take the antiderivative, and what I'm going to do is I'm going to write it with taking it the antiderivative with respect to x, so dx. And we end up using the notation from Leibniz, which was this elongated s. So that's the symbol or the notation for it. So it's this elongated s, and we'll get to talk a little bit more about why he's using the long s, but it's to kind of give the idea of a summation. So the s was standing for sum. But we will explore more of that later. For right now, we're just looking at the antiderivative as kind of the reverse of differentiation. So this is our symbol for doing the antiderivative, and this tells us with respect to x. The question is, will we always add the c when we write an antiderivative? So the question is, do we write c for the antiderivative? All the time. Not necessarily. The reason for that is because you write that constant of integration, or that c, sorry, that constant, you write that c if you are missing that information. And we will we'll see an example later. But it's a good question. Yes, we're going to get to that. Okay. So what we should do is I will give a definition. And that's the definition in the book, and it's an antiderivative for f is a function, and they use a capital F, such that they use capital F prime of x is equal to little f of x. We write so they're using a capital F is equal to that long s f of x dx. Okay. Now, this is where we can introduce some terminology. This is called the indefinite integral of f This tells us f is the integrand, or the function that we're integrating. And that tells us with respect to x. I suspect we'll add the c if there's logically b1. For example, finding the inner of population growth. Most cities don't start at 0, so it should probably have a constant. Yes, so there's some sort of initial value. And that's what we'll call initial value problems. But we're adding back information into it that if we were just taking the straight antiderivative, or as I've also called it, the indefinite integral, or the integral, we've lost some of that information. So when we put in that initial value, we can actually figure out what that constant is. So I better also then give a little name. This is called the constant of integration. Okay. So let's do some basic rules. Now, I think they might have called it antiderivative, but antiderivative integral are interchangeable. So we were already introduced to one, which was the power rule. So again, for this, it's that we're going backwards. So in terms of the derivative, we're dropping down a degree. In this case, we're going up a degree. So it goes from n to n plus 1. And also, the n plus 1 goes into the denominator, plus our constant. And this only works for n not equal to minus 1. Because the reason for that is if I put minus 1 in here, it works. This would go x to the 0, but the problem I have then is minus 1 plus 1, I have 1 over 0, so this doesn't work anymore. But what about negative 1? And that would be like, hey kid, we're getting to that. We'll eventually get there. Just wait. We will do it. Now, the constant multiple. Let's do down here, constant multiple. Now, we remember that when we had the derivative, say I had d by dx of k times f of x, that was just simply k times the derivative of f. So k is it's a constant. We can actually pull it out, or you can think of it. So same thing with the constant multiple for integrals, that if I have some k times f of x, and I'm going to integrate or take the antiderivative with respect to x, that is very similar to when I'm taking the derivative, I can actually pull that k out in front as well. So k times the antiderivative or the integral of f of x dx. So if I called this, say 1, here's 2, I'll call this like, let's take a little pause for a second, that I can actually combine 1 and 2 together. So I can have the constant multiple in power rule. So if I take that, I have k, and it's times, instead of f of x, it's going to be x to the n. I'm taking that with respect to x. Then the k comes out in front, and I'm left with x to the n dx. And then I can substitute in, so this is by 2, and then k times 1 over n plus 1 x to the n plus 1 plus a constant. And that's by 1. Yeah, or if we had a graph where our line crosses somewhere that isn't the origin. Yeah. Yeah, I would, yeah, basically, yes, that's right, Maple. Okay, so we did that that combination one. So that's not a strict, this is just a combination of 1 and 2. So like mathematicians are always trying to get it down to the bare basics. But this could be useful for you. So that's why we'll write that one out. Number 3, the sum rule. Now in derivatives, we had d by dx, and I had f of x plus g of x. That's equal to, again, we can distribute that operator. So then I got df by dx plus dg by dx. And that's the sum rule. Remember, it doesn't work for the product rule, but it works for the sum rule. It works for the sum. So the same idea happens for the integral or anti-differentiation. So if I take, there's my long S, and I have two functions, f of x plus g of x dx. And again, I can kind of think of distributing that operator on each term so that I get the integral or the antiderivative of f of x dx. So I'm taking the integral of f with respect to x plus the integral of g with respect to x. Now you can also, there's the corollary, and the corollary is just kind of like a consequence of the sum rule. Then you have like the difference rule. So I'll have f of x minus these two. And so that instead of the addition of the two integrals, it's a minus. Oh, can you explain what the by 1 and by 2 means in the constant? Oh yes, I was just writing, here's 1 and here's 2. So what I've done here is combining the constant multiple and the power rule, so that I had a k times an xn. I pulled out the k. This is by the constant multiple rule. And then I applied to this part right here the rule 1, and that's how I get that. So I was just writing down the justification for that. Okay. Let's do number 3. Okay, let's do some examples. So here's A, and so let's do that x to the 4th, and we're going to take the antiderivative or the integral with respect to x. So using our power rule, oh good, I have enough space. So I have x, so my n is 4. So in this case, you can think of that as n is equal to 4, and using power rule, the exponent goes up by 1, so it becomes 4 plus 1. And I also need to write 1 over n plus 1, so in this case, it's 4 plus 1 plus a constant. We can get rid of that. And cleaning that up, I'm left with 1/5 x to the 5th plus a constant of integration. Okay. In this one, I can use my constant multiple and power rule, and so that's telling me that it's k 1 over, oh look at that, I can do that. So that's what I'll do. I'll write out the 2, I'll bring the 2 out in front, and I'm left with x to the 5th dx. And then I can apply my power rule, so then I get 2 times the x goes up by 1, so it goes from 5 to 6, and the 6 also goes into the denominator. And we can simplify that, so it's 2 times 1, 6, or that's equivalent to 1/3 x to the 6th plus c. For part C, or for our example, our third example, what we're going to do is x to the 4th plus 2x to the 5th. And we're going to integrate that with respect to dx. Now by the sum rule, I can apply the integral to each individual term. So I get the integral of x to the 4th plus d with respect to x, plus the integral of 2x to the 5th with respect to x. So that's by the sum rule. And we've already solved that, so I'm going to just write that again. So I have 1/5 x to the 5th plus, in this case it's 1/3 x to the 6th plus a constant. So in there, that's by A. And for there, that's by B. Now notice these are C's here. The C's, it doesn't really matter at this point right here. It's just to tell me that there is a constant of integration. This necessarily does not mean that it's the same C in this one. Okay? You know, again, this is where I would be okay with seeing something like that, but sometimes the book may perhaps come up with something different. They could say, I don't know, they factor out this x to the fifth because there's an x to the fifth factor in there as well. So, you know, writing something like this, you know, it's possible, but just keep that in mind that I'm okay with seeing something like that. I don't really see a point in, unless, you know, it's useful for your problem that you're trying to solve. And what we'll see later is when we start to get into the applications like optimization, or if we get into some of like elasticity, or some of the other business administration and economics applications, reducing it down to something simple or manageable is good, because eventually we might have to take another derivative, or we might have to manipulate it or solve for something. And it makes it a little bit more difficult if it's in a form that we can't handle. So, you know, again, it depends on the tool of analysis that we're using for the problem that we're using it for. I know that was kind of sounds wonderfully vague, but that is as best as I can describe it at the moment, but we will eventually see some problems where we will have to simplify. Okay, so what I was doing that, I was just applying the difference rule. So, applying the integral to each term, and then the only thing that's different from this one and this one is the minus. And again, I have already solved 1 and 2 here, so again I can just write 1/5 x to the fifth, or sorry, maybe I'll put this as a, and here is b, minus 1/3 x to the 6th plus c. So those were examples that we were doing, just illustrating those kind of basic integral rules. We had the power rule, the constant rule, and then we also had the sum rule. Okay. So this is page 4. Okay. So let's just talk a little bit about like physical problems. For instance, we could say have position. So like there's a position of a car, and we can think about a car. So it has a position at a certain at a certain time, and the change in position, or how fast the change of position is what we call velocity. And that's the derivative, or to get to this, we differentiate. So if we had some function, and we'll say x of t, then if we differentiate, then we get the velocity function. So what is the velocity? It is the rate of change in position. Now, if we differentiate again, then what we get is the rate of change in velocity. And this is what we call acceleration. And yet again, if we differentiate, we can have the rate of change in acceleration. And that is called the jerk. And I don't remember what usually the variable that they use for that. So from the position here to the velocity, that's the first derivative. To get to the acceleration, that's the second derivative of the position function. And to get to the jerk, that would be the third derivative of the position function. So we can do that with derivatives. So we're looking at the rate of change in position, the rate of change in velocity, the rate of change in acceleration. Sometimes we've gone in one direction. Maybe we want to go in the reverse direction. So, same idea. Starting at the jerk, which is the rate of change in acceleration, we can actually integrate. To get the acceleration. And again, if I had the acceleration and I integrate, I get back to the velocity. And again, if I integrate or undo, kind of looking at the change that we were looking at, the change in position, if I integrate, I get back to the position function. So you can bounce back and forth between these. Now let's do, So I think I was writing out some of those. So if I had x of t, that's the position at time t. V of t is the velocity. And we have a is acceleration at time t. Well, what I was saying here is that, for instance, velocity is the derivative of the position. So I can write that out. That v of t is equal to the derivative of the position function with respect to time. Now if I integrate, let's say I apply or I do the antiderivative. So I do the antiderivative on both sides. So what you get then, and I'm going to integrate with respect to time. So again, I apply the integral on both sides. what you notice then is I'm integrating, well, basically this x comes out in front, but these dt's cancel, and I'm just left with x. And so that's what we were expressing before, that the integral of the velocity is the position function. So if I have the velocity and I integrate, it brings me back to the position. Same if I have acceleration. I have dv, so it's the change in velocity over the change of time. Integrating it, again, with respect to time. So I apply the integral on both sides. And I have the dv by dt. So again, what this is saying is that the integral of the acceleration is the velocity. So let's do an example. And this is following example 11 from the book, page 131. I think I changed it just a little bit because it was using gallons and we're going to use liters. And I think we weren't able to solve it using just those rules that we were using. So we have water is flowing into a tub at 3t plus square root of t, and that's liters per minute. So that's a rate. After t minutes. Then the question is how much water, because again, this is kind of rate, so kilometers per hour, we have liters per minute. So what they're going to ask for is how much water is in the tub after 4 minutes if it started out empty. This is where Mr. Walker would have said, there's the additional information if it started out empty. That's the additional info needed for C. Okay. So what we were given we're actually given kind of like this derivative. So we have f of t is equal to 3t plus the square root of t. And what we're required to find is f of t. So again, we're going to have to integrate or find the antiderivative. So if I take the integral of this f prime of t, of dt, dt, then the next thing that I can do is, using our sum rule, I can apply that integral to each of them. And again, I can pull out that 3, and so I'm left with the integral of t dt plus the integral of, we have a square root, so again, what I can do is change that into an exponent, and that will be 1/2. So now I can do the integral of that. So that's just t, so it's t, it goes up from 1 to 2, and also the 2 goes into the denominator, plus, then I have t. Now in this case, I need to go 1/2 plus 1, which gives me 3/2. And into the denominator I write 1 over 3/2. Now equivalently, 1 over 3/2 is equal to 2 over 3. So then I have 3/2 t squared plus 2/3 t 3/2, and I have a constant of integration. I wrote the c also up here as well because as soon as I take the integral, I have to have a constant of integration. So there is the c. Let's see, should I? That's there. Okay. Okay, so we also know that f at 0 is equal to 0, and that's since the tub is empty. Initially. So what does that mean? We then sub in those values. So I have f of 0. So here's my f of t. So I have 3/2, and 0 is substituted in there, plus 2/3. I have 0, 3/2, plus c. And we know that this was equal to 0, so all of that. This is 0, this is 0, so what I'm left with is that c is equal to 0. So f of t is equal to 3/2 t squared plus 2/2 3t to the 3/2. And I don't have to bother with the plus c anymore. I've already solved for what that constant is. Okay, but the original question said how much water is in the tub after 4 minutes. So this is the we've solved this part. So we actually got the function of water at time t. So this is the function of water in the tub at any point, at any time t. So that means we're after 4 minutes. We're asked for after 4 minutes. So after 4 minutes, t equals 4. Then what we are looking for is f at 4. So you get 3/2. So put that over that side there. So I get 3/2, 4 squared plus 2/3. I'm substituting in that value of 4 again. 3/2. So I get 3/2. 4 squared is 16 plus 2/3. Okay, so I have 4/3. So 4 to 3/3 is equal to 4 to the square root. So that's the half part. I should maybe write that out. So what I'm saying is this times 3. So I can actually break that up. So there's the half, and then let's do the 3. So root 4 is 2. 2 cubed is 8. So 4 to the 3/2 is 8. So 16 times 3. So think of that, 16 gig memory cards, 3 of them. That is 48 gigabytes divided by 2 plus 8 times 2 is 16 over 3. 48, that's 2 2/4s. And I have 16 over 3. I have to rewrite that over 3 again, so 24 times 3, so that's 3 2/4s, or that's 72 cans. 72 plus 16 is 88. Okay, so that's how much water that there is. Therefore, there's 88 over 3 liters of water in the tub at t equals 4 minutes. Oh, and that also means a therefore. Just in case. Is there any questions about that? It's been pretty quiet in the chat, so just to check in. Is everyone okay with that? Okay, excellent. What else can we do? It's kind of cool with how much, with just kind of 3 simple rules, how much we can do with kind of reversing the derivative. But again, when we differentiate, we do lose some information. So again, if we're going to reverse that, or we're going to do the integration of it, we'll have a c, and we'll need this kind of additional info, or this initial value, as it were. to be able to help us to figure out what that C is. And if you don't have that information, you can't do it. So it's just C. Okay, what else can we do? There was an example in the book, but I think I would write it out a little bit longer. And this was following example, I think, 9 in the book. In the text. And that's in the section on the antiderivative. So what they were saying, or what was the question, was find, and then they have the integral of x cubed minus 8 divided by x minus 2 dx. So again, it's the integral of x cubed minus 8 divided by x minus 2 with respect to x. Okay, so what we do as we kind of go through our pages that we got, we've done all this work. We don't seem to have rules to handle this part. We don't have any fractions, or we don't have any rational functions. So what can we do? So none of the rules apply directly. Well, we're not stuck yet. We're going to do it. We're going to do this. And so the way that we're going to do it is we're going to simplify it first. So what we're going to do is basically what we used to do in elementary school, which was if I had something like 3 over 2, and I'm going to do a division. Well, 3 can't go into 2. So what we used to do is, fill out, and we would do what we'd call long division. So and in this case, that would be 2/3. So how many times does 3 go into 2? That's 0 times. How many times does 3 go into 20? Well, that goes in 6 times. So that's 18. And I'm left with remainder 2. And I'm still not done yet. I have 20. And again, 3 goes into 20 6 times. So again, 18. And then I'm left with 2. And so again, I just keep applying the same thing. So I got 6 goes into 3. 6 times 3 is 18. Okay. You're probably going, why are we doing this? Why are you reminding me about long division from elementary school? Same idea of what we're going to do here. We're going to divide x minus 2 into that polynomial x cubed minus 8. So this is using long division. I have x minus 2 And what I'm going to do is I'm going to have some placeholders. So I have x to the 3 plus 0x squared plus 0x minus 8. So at this point, I have x minus 2. And so what I can do is pick, say, something like x squared. So that at this point, x squared times x minus 2 is equal to x cubed, so I distribute that, minus 2x squared. So I write that down. X cubed minus 2x squared. Okay, so it's going to be all of this, and we're going to subtract. So I have x cubed minus x cubed, so that's 0, so I don't have to worry about that. And then I have 0 minus 2x squared, so I'm left with 2x squared. Okay. Then the next thing I need to do is figure out what kind of goes, how many times like x minus 2 goes into 2x squared. And so what I can do is, so that's kind of for this part. This one is 2x, and the reason for that is I have 2x times x minus 2, which is equal to 2x squared, and then that's 2x times minus 2, so that becomes 4x. So I bring this down. And then I subtract that. So 2 minus 2, that's 0. And I have 0 minus 4, so that's 4x minus 8. And the last thing that I need to do is, how many times does x minus 2 go into 4x minus 8? Well, again, the trick is I'm just looking at these kind of terms right here. I have the x and I have an x here. But what's different is here is I have a 4 and there's not a 4 here. So I'm going to multiply that basically by 4. So plus 4. And so at that point, I have 4 times x minus 2. So that's 4x minus 8. And that's 0. Okay. So after doing that long division, what does this get me? This tells me that x cubed minus 8 over x minus 2 is x squared plus 2x plus 4. Okay, well, you're like, okay, so what? Oh, the nice thing is that while I don't have a rule for this one, if I integrate x squared plus 2x plus 4, this is something that I do have a rule for, that I can integrate x squared dx plus I can integrate 2x dx plus the integral of 4 dx. So, using our power rule, I have x cubed, and the 3 goes into the denominator. I have 2 times, and this will be x squared, 1/2 there, plus, now this is interesting at this point. We haven't done something where we are integrating a constant, so there's 4. What you can think of that as, let's say 4x to the 0 dx. So x to the 0 is 1, but that means then if I'm going to integrate that, that goes up by a degree. So that goes from x0 to x1. So there's my constant. I can factor that out. And so now I'm just left with x plus c. Now, if you're not convinced about what I said there, I have 4 there, and here's 4x. Well, if I take the derivative of that, the derivative of 4x is just then 4. So it works. And that is the end of that question. Oh, no. Oops. I have 2 over 2. So that can simplify down to 1/3 x cubed plus x squared plus 4x plus c. Okay. I take it there's no value in factoring the equation. I don't really see any value to it. I think this is in a good enough form, and if I remember correctly, kind of this is what the textbook would write it as. Sometimes, you know, they might write something like they just, instead of writing that third, they'll write it like that. But other than that, I don't really. Oh, okay. That's a different question. Excellent. So that was the question. So the question was, so after the long division, we got x squared plus 2x plus 4 oh, okay. Yeah. So after the long division, we got something like that. He was saying that if we had something where we got to the point of, let's say that it was like ax plus 2, and then we had it somehow like squared. And that would look something like this. So if we had got a kind of a polynomial like that, we could somehow simplify it like that. Again, the issue that we have then is, now I would have an integral like this, and I don't have any rules to apply to this at the moment. So using our basic integral rules, I can't This is just x. This is not for a function. So it's just x. Here is a function, but this is only for me to pull a factor of a constant out. And this is a sum rule. It's just being applied to f and g. I don't have a way to handle this. The only way that I can do that then is I would have to expand it out. So I would have to do something like this. Now, it would be nice if we had a little bit more powerful tools. We'll get to it, but yes, we can't, using our rules, directly apply to this and integrate it. So, yep, we'll get to it. Yeah, it'd be nice if we had something like reverse chain rule, right? Like something that we can handle where we have compositional functions. There's a good idea, isn't it? Like somebody's thinking. It'd be nice if we had some sort of reverse chain rule, and that is a different method of integration, which we'll hopefully get to. Okay. So here's an example. We're going to do, we have a particle. Oh, I don't know. You can think of a particle, or you can, yeah, let's do a particle, or I don't know. You can even, basically particle is just like some sort of dot. Anything, you can just replace it. So a particle is accelerated in a line. So it's going woo. Okay, so that its velocity and we're going to do it in meters per second. So that's the velocity. So if you're used to thinking of kilometers per hour, again, it's just meters per second. That's velocity or speed. And that's equal to the square root of time elapsed and that's measured in seconds. Then the question is how far did it go? Or how far does, it says how far does the particle travel in an hour? And they're a little bit more specific. So in the first hour. Okay. Yes, that sounds like foreshadowing. I didn't mean it to sound like it was for like some foreboding specter over this, but these are good questions, and of course we ask those and we keep playing with them, and can we do this? And we keep playing with it until we break something. As for this example, it says how far does the particle travel in the first hour? So it says we're told that the particle is accelerated so that its velocity. So we're told that the velocity is equal to the square root of time elapsed. So it's just square root of t. That's not too bad. So what does that mean? Oh, well, we can, using our rules, we can probably write that as t to the 1/2. And then, so that implies that the derivative of the velocity, it's the derivative of the position, is, or you can think of it as dx by dt is equal to the square root of t. And then we integrate this. So to go from this derivative, we're going to integrate with respect to t. And again, very similar to what we did previously. Did I? All right, I will do it again. T. So again, it's 1/2 plus 1. So that's 3/2. And then 1 over 3/2, which is 2/3. So 2/3 plus a constant. Now the thing is that he didn't tell us any more information about this. So let's say, assuming x of 0 is equal to 0, then well, if I substitute that 0 into that, so I get x of 0 is equal to 2/3 times 0, 3/2 plus c, and that should equal to 0. This goes to 0, so c equals 0. So then it follows that the position function is just 2/3 t 3/2. Now, the question that we were asked for is how far does it travel in the first hour? Wow, there's a mismatch in units because we were measuring in meters per second, and we found what the velocity was. So we actually found in this case, this is the distance meters, and that's where the time is in seconds. Okay, so very sneaky about them, because again, it's measured in seconds. And then they asked us what the first hour is. So what does this mean? Well, in an hour, well, there's 60 seconds in a minute. And there's I really hope people know that it's okay. Yes, it's 3. Yeah, that's good. There's 60 minutes in an hour. So I'm just working this out. So it's 60 times 60, or it's 6 times 6 is 36, 2 zeros, and I have it in seconds per hour. So 3,600 seconds per hour. So at t equals 1 hour, or 3,600 seconds, my x of t, or that's 3,600, is equal to 2/3 of 3,600 boy. Square root of 3,600 is 60, right? And I'm cheating. And this is why I did it, because I know it's 60 times 60. There we go. So that means that the square root, see? I wasn't in too much deep water. Then I have 60 cubed times 2 over 3, which works out to 144,000, and what are my units? Meters, right? Because it's accelerating along the line. So, just to finish off the question then, therefore, the particle travels 1,444,000 meters in the first hour. Okay. So, is there any further questions about that? Let's see, I think this was page 8. Let's just recap what we had covered. Hopefully I have these sheets in order. So again, we covered the basic integration rules. We had the power, the constant multiple, and the sum rule. We were able to, here are some straightforward examples where we're applying the rules. We showed that we had position, which was a rate of change in position. Velocity was a rate of change. The rate of change in velocity is acceleration, and acceleration to the rate of change in acceleration is the jerk. And again, we're differentiating. Remember, each time we're differentiating, we're losing some information. So if we are going to go backwards, we'll have to inject some information back into it. We did some flow, and we integrated the flow rate to find out how much water is going into a bathtub. Oh, there's page 1. We had an example where we couldn't quite apply the rules directly, so again, none of the rules applied. We simplified it. We used some algebraic manipulation to get it back to a form in which we can apply the rules to. And lastly, this example kind of just illustrates, be careful in a mismatch of units. So for instance, we were working with meters per second, and we had time elapsed measured in seconds. And then the question, they threw a curveball, which was, they asked us an hour, which is a different unit of time. So again, we had to work out what that unit, convert this unit into a unit that we could plug it back into our original function. And then, of course, this is what we get. And again, I usually will write out a final statement. And the reason for that is because a lot of people don't want to look at the math. They want to know what the answer is. Sometimes they don't want to know your workings. So again, a final statement, you know, they might look through all this. They see lots of symbolic manipulation. They get 144,000 and they're going like, I don't know what this means. I don't know what that X means. Why is there 3,600? They can start getting angry because they're like, that's not what I asked you. Again, wrapping it up nicely. Okay. Well, I hope everyone took some anti-differentiation or anti-derivatives or integration, and we'll do some more of those eventually. I put some of those on the assignment. So assignment 4 is, are we on 5 now? We're on assignment 5. So assignment, let me double check what number I'm on. I think because we had quiz 4, we should be on quiz 5. Sorry, assignment 5. So again, here's assignment 5. Let me just switch over to my 2 of these. So again, here is my screen. So again, here's our assignment. Please note we have a test on the 25th of February 2021 during class time. So what I've done is I've given you some exercises for antiderivatives. We're going to do some, we covered some of these questions before in terms of cost revenue functions. So this one says to do example 12. I've written out the question, but if you're asking for a solution, it's in the textbook. It's example 12, page 107. We're going to do a little bit more rates, velocity, and acceleration on Thursday. And then I think on the next Monday when we're back after reading week, we'll do one more, one more topic. The other thing is that I'm not going to have a quiz the week of the 25th. So no quiz on the 23rd. We have our test on the 25th. And then also below what I've given you is some review questions. So they're from the review section. So this is kind of like from the review chapter. So there's a couple of questions from there. This is chapter 1 where we're doing derivatives limits and derivatives. And then this is also, we're using the definition of the derivative. So again, the definition of the derivative is, if I can switch back to my camera. Again, the definition of the derivative was using that delta x of the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So just that. So there's some questions to do with using that, finding the derivative using that definition for those, examples. And then chapter 2, that's with rates and, second derivatives. And I think there might be some integration in chapter 2 as well. So hopefully we'll have enough time to, and I see some questions. Will all assignments up to assignment 4 be covered on test 1? All assignments up to assignment 5. Yeah. So up to assignment 5 we'll be covering it. And again, exactly. Again, if you guys are working over the reading week, everyone, I mean, gentlemen and ladies, if you're both working over the reading week, feel free to send me an email. If there are a lot of questions or whatever, we can set up, even I can keep my office hour during the reading week and answer some questions then. But again, email is, I'm just an email away. Send me a question, or if you're stuck on something, I would recommend, if you are working on a question and you're getting stuck, show me some of the work. Send me, write out some of the material and then kind of like circle something or put a question mark, just take a picture with it with your phone or scan it, send it to me. And then I can, maybe I can annotate it or make a suggestion. So, I don't want you guys to feel that you're stuck or you don't have any help over the break. And again, the assignment questions, what we've covered in class, should be indicative of what will be is on the test. Okay? And on that, I'm going to conclude. Thank you all for tuning in on lecture 14 of MAE 113. My name is Richard Kohar. You know my email. So have a good night.